Welcome to Lecture 13. This is 3.4, Measures of Position and Outliers. So the first thing we'll look at is determining and interpreting z-scores. By definition, the z-score represents the distance that a data value is from the mean in terms of the number of standard deviations. We find it by subtracting the mean from the data value and dividing this result by the standard deviation. There's both a population z-score and a sample z-score. So the population z-score is going to be z equals x minus mu over sigma, or standard deviation. The sample is z equals x minus x bar over s. And the z-score is unitless. So there is no unit associated with the z-score. It has a mean of 0 and a standard deviation of 1. Let's take a look at the first example. Determine whether the Los Angeles or the Colorado Rockies had a relatively better run-producing season. The Angels scored 773 runs, so that's supposed to be a 3, and play in the American League, where the mean number of runs scored was mu equals 677.4 and the standard deviation was sigma equals 51.7 runs. The Rockies scored 755 runs and played in the National League, where the mean number of runs scored was 640 and the standard deviation was 59.9 runs. Alright, so to determine which team had the relatively better run-producing season, we're going to compute each team's z-score. The team with the higher z-score had the better season. And because we know the values of the population parameters, we can compute the population z-score. Let's go ahead and do that. Angels and the Rockies. So the Angels z-score, using our formula we were given above, and then we'll go ahead and plug in our values. So we had x was 773. Let me just go ahead and color those in. X was 773, and then we need to find our mean, which was given as 677.4, and then divided by our standard deviation, 51.7. And that gives us 1.85. Okay, now let's look at the Rockies z-score. Once again, x minus mu divided by sigma. Finding those values. So my x value for the Rockies is 775. Then my mean value, and lastly, my standard deviation. Okay, plugging those numbers in. Oops, I forgot to highlight them. Let me do that real quick. Highlighting. Okay, so plugging those in, we have 755 minus 640 divided by 5.9. Plugging that into our calculator, we come out with 2.06. So what do we have here? Well, the Angels had a run production of 1.85 standard deviations above the mean, while the Rockies had a run production of 2.06 standard deviation above the mean. So, which one was higher than normal? Which one did better? This one was only 1.85 above their mean. The Rockies, on the other hand, were 2.06 standard deviations above their mean. So the one that did better was the Rockies. So we'd say the Rockies had a relatively better year because their z-score was higher. Period. And box that off. Ooh, getting a little messy there. Alright, now let's look at Objective 2, interpreting percentiles. Okay, so recall that the median divides the lower 50% of the data from the upper 50%. Remember, if you're looking at the bell curve, your median's right there, and then you have your 50 and 50. The median is a special case of a general concept called the percentile. By definition, the kth percentile, denoted p sub k, of a set of data is a value such that k% of the observations are less than or equal to that value. Okay, so percentiles, let's look at this example too. Percentiles divide a set of data that is written in ascending order into 100 parts. Thus, 99 percentiles can be determined. So let's take a look at an example of this. If we have a data line, and I don't know how long it is, so I'm going to go ahead and put ... in between. Don't know how long it is. But we have the smallest data value, and we have the largest data value. So notice this is in ascending power. The data grows larger in that direction. If we go ahead and split this into our percentile, so p sub 1, p sub 2, so on until we get up to a p sub 98, and then p sub 99. Now notice this would be p sub 100. If we look at this, anything in this interval would be the bottom 1% because it is less than 1, percentile 1. Then, if I took a look at the next interval, which would be this one right here, up to P2, that would be the bottom 2%. Or, I could even take a look at everything below 98, and that would be the bottom 98%. Another way I could look at it is I could look at right here, this interval here, and that would be the top 1%. Why 1? Because that's only a 1% interval. Another way I could look at it, I could decide I wanted to take the top 2%. So higher than P98. Okay, so that's sort of how things are split. We don't always use all 99. In fact, normally there are certain ones that we look at, which would be the quarters. So 25%, 75%, 25, 55, 75. A lot of the times when people have children, you'll notice they put their height and their growth charts in percentiles. For example, one of my nieces is in the 75 percentile for height. So she's in that range. Another niece of mine is actually off the chart for height. And funny enough, they are siblings, so it'll be interesting to see what their height ends up as. So percentiles are often used in growth charts to see how your child matches up with the rest of the population. Now let's take a look at example 3. Jennifer just received the results of her SAT exam. That should be SAT. Hopefully I fixed that on your notes. Her SAT mathematics score of 600 is in the 74th percentile. What does this mean? Okay, so what should we do? Well, the kth percentile of an observation means that k% of the observations are less than or equal to the one we just saw. So, what do we have? Well, we have a percentile rate of 74. 74. So this means that 74% of SAT math scores are less than or equal to 600. Okay, so if 74% of the exams are less than or equal to the point she got was 60%, what percent of the people got higher than 600? Well, you'll just take 100 and you minus the 74 from there, and you would get 26. So this means, 26% of the students who took the exam scored better than Jennifer. So if we took a look, for example, at that number line we were looking at for the scores, if we split this into quarters, so 25%, 50%, 75%, 100%, her score is inside the 75th percentile. And people who scored above her are over here, somewhere higher. In the top, well, okay, so not 75 exactly because she had 74, but they're up here above in the 26th percentile, the students who scored better. Objective 3, determine and interpret quartiles. So the most common percentiles used are quartiles. Quartiles divide the dataset into fourths, or 4 equal parts. The 4 parts are illustrated as follows. Kind of like just what I drew right up there. So if you split your dataset up, you'll have Q1, quartile 1, Q2, quartile 2, also your median, Q3, and your largest data value, and your smallest. Okay, so these are the main quartiles that we just tend to split things up. Like as I mentioned, in terms of children and growth charts, when you go to the doctor, they normally tell you where your child's height falls in the quartiles, or maybe where sometimes they think they measure the circumference of a child's head, and other things that they chart with your child. So in this interval here, we have 25% of the data. That's in the 25. Then in the next interval, we have another 25%, another 25%. Let me go ahead and write 25 right there. And the other 25%. Alright, so example 4. The Highway Loss Data Institute routinely collects data on collision coverage claims. Collision coverage insures against physical damage to an insured individual's vehicle. The data below represent a random sample of 18 collision coverage claims based on the data obtained from the Highway Loss Institute. Find and interpret the first, second, and third quartiles for collision coverage claims. Should be a nice comma right there. So how do we do this? So for finding quartiles, first we want to arrange the data in ascending order. Alright, so I'm going to pause the video and arrange it, and go ahead and pause with me and check your work with mine. Alright, so I've done the first step for finding quartiles. I've arranged the data in ascending order. Now the next step is going to be determining the median, or the second quartile. So the median, as usual, is the middle number. How many numbers do we have? Well, we have 1, 2, 3 across, so 3, and then 1, 2, 3, 4, 5, 6. So we have 18 numbers. Okay, that's an even number. So to find the median for an even number, you're going to take the middle 2 numbers and then divide them by 2 to find your median. So what are the middle 2 numbers? For 18, that would be 9 and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9th number and 10th number. We're going to go ahead and add these. Then divide by 2 to get my median. So the median is going to equal, or the median, which is also Q1, or Q2, excuse me. That's going to be 1657 plus 1953. Divide that by 2. And what do we get? Putting that in the calculator, we get 1805. So that's Q2. Easiest one to find first is actually Q2. From there, we can go ahead and find Q1. So Q1 is the middle of the first. Now I just noticed these two are written in the wrong place. The 802 and the 735. Let me just quick scan this and make sure the numbers are in ascending order. Okay, it looks good. So the middle number here is going to be, Q1 is going to be the middle number. So Q1 will be the middle of the first half. And the middle number for the first half is 735. Oops, wrong pen. And then Q3 is very similar to finding Q1. We look at the top half. So that'll be these numbers, and the middle number of these top half is going to be 4668. So 4,668, the middle number of the top half. Okay, so we have our quartiles. Q1, Q2, and Q3. I'm going to go ahead and write them out a little nicer over here on the side. Q1, 735, Q2, 1805, and Q3, 4,668. Now, interpreting this. Well, it looks like for Q1, which is, remember, the 25%, I'll go ahead and write that down. 25%, that's the 25% marker. This is the 50% marker. And Q3 is the 75% marker. The first one is saying that 25% of the data, so 25% of the claims, is less than or equal to $735. Then, looking at the middle one, we know that 50% of the claims should be R, less than or equal to $1,805. And lastly, 75% of the data, or of the claims, are less than or equal to $4,668. Note, you could also say that this means that 25% of the claims are greater than the 75%, which is 4,668. So if I drew a quick little graph up here, I'm going to go ahead and do this really quick here. We have Q1, which is 735, Q2, which is 1805, and Q3, which is 4,668. So we know 25% of the data, right here, 25% of the amount of claims was greater, 25% of the claims in terms of dollars was greater than 4,668. And you could also say 50% of the claims were greater than $1,805. Or 75% of the claims were greater than $735. Many ways to look at this data. And for examples on how to use technology to find the quartiles, you can go ahead and look at page 151 of the textbook or email me. And let's see, Objective 4, determine and interpret the interquartile range. So what is that? Well, so far we have discussed three measures of dispersion: range, standard deviation, and variance, all of which are not resistant. Quartiles, however, are resistant, which is really nice. So for this reason, quartiles are used to find a fourth measure of dispersion. And this fourth measure is called the interquartile range, or short way of saying it, IQR. And this is the range of the middle 50%. Another way of thinking of that, what does the middle 50% look like? That would be something like this, 50%. Looking at the data, that's sort of right there in between all of them. So all the extreme ones we would ignore, and all the other extreme ones we would ignore. The formula for this IQR is equal to the third quartile and the first quartile. So subtract the first from the third. All right, we're going to determine and interpret the interquartile range of the collision claim data from example 4. Let's go ahead and, real quick, to do that, for the IQR, we need Q3 and Q1. And what were those? Let's take a look. Q3 was 4,668. And Q1 was 735. Now let's see, subtracting those out, what do we get? We get 3933, and we could go ahead and include the dollar signs there for the units. What does this mean? This means that the IQR, that is the range of the middle 50% of the observations in the collision claim data is $3,933. Okay, one thing to always remember is that finding the information is great, but interpreting it is also really important, especially for statistics. So for the exam, always take a look at how things are explained, because more than likely I'll be asking you to explain what your data means or what you found and what does it mean in context. Alright, next. Note, when the distribution of the data is skewed or contains extreme observations, it is best to use the interquartile range as a measure of dispersion because it is resistant to extreme values. Any conclusions drawn from a set of data that contains outliers can be flawed. Okay, so checking data for outliers. How do we do this? When performing any type of data analysis, we should always check for extreme observations. In the data set, extreme observations are referred to as outliers. Outliers can occur by chance because of error in the measurement of a variable during data entry or errors in sampling. There are many ways that outliers can occur. For example, in the 2000 presidential election, the precinct in New Mexico accidentally recorded 610 absentee ballots for Al Gore as 110. Workers in the Gore camp discovered the data entry error through an analysis of vote totals. So that's an example of where data can be skewed. But there are times when data is not skewed, and there is a strange outlier. But outliers do not always occur because of error. Keep that in mind, as sometimes extreme observations are common within a population. For example, suppose we want to estimate the mean price of a European car. We might take a random sample of size 5 from a population of all European mobiles. If our sample included a Ferrari F430 Spider, which I don't exactly know what that looks like, which is approximately, and that is a nice looking chick, it would probably be an outlier, because this car costs much more than the typical European automobile. The value of this car would be considered unusual because it's not a typical value from the dataset. So if, for example, this car passed by when you were sitting there on your chair, recording the 5 cars that go by, your data would really be skewed, because more than likely the other cars that pass by are not that expensive, unless you're sitting near some millionaire housing. And then that wouldn't even be the normal population in general. So let's see, how do we check for outliers? Well, the first step, determine the first and third quartiles of the data. First and third quartiles. So Q1 and Q3. Second, compute the interquartile range. Compute IQR, which, recall, IQR is equal to Q3 minus Q1. Third, determine the fences. What are fences? Fences are the cutoffs for determining outliers. So lower fence, which I'll just abbreviate for LF, would be first quartile minus 1.5 times whatever your interquartile range is. The upper fence, UF, is going to be Q3 plus 1.5 times your IQR. All right, and then step 4, if a data value, let me go ahead and back up on that. If a data value is less than the lower fence, remember abbreviated, or greater than the upper fence, it is considered an outlier. And as usual, people created these boundaries. So that's one thing to keep in mind with statistics. It is sort of created by what people decide is considered an outlier or not. And you mark an outlier with the asterisk. So for example 6, we're going to check the data from the Highway Loss Data Institute for any outliers. Okay, so for the steps. The first step was we need to use the quartiles. So step 1, using our quartiles, which we had from our first, or from all the examples we're using. Q1 was 735, and Q3 was 4668. Now, step 2, we're going to find the interquartile range. So IQR is Q3 minus Q1. Q3 is 4668, remember right there. Q1, right there, is 735. And remember, this data we found earlier in the previous examples. This comes out to be 3933. And boxing our information is always a good idea. Step 3, finding the lower and upper fence. And you're allowed to use the abbreviations when you're showing your work. Q1 minus 1.5 times IQR. So Q1, 735, minus 1.5 times my IQR, which I found was 3933. Plugging that into our calculator, we get negative 5164.5. I have a feeling none of the data values up here were in the negatives. So it doesn't seem like we have any extreme values there. And finding the upper fence. That's going to be Q3 plus 1.5. Oh, notice my 3 got a little high there, so I like to bring that down. I don't want to confuse it for an actual 3. Back to the work. Q sub 3 plus 1.5 times my IQR, which is 4668 plus 1.5 times 3933. That's going to equal 10,567.5. Alright, so now what we're going to do, let's see if there are any outliers. Well, as I mentioned before, this is a negative value. None of the claims are negative because that wouldn't really make sense for the money for claims. Alright, so none of the data, so no data is below the lower fence, period. Let's see. Anything above 10,000. Oh, look at that. We have found one above 10,000 right there, the 21,000. Anything else? Nothing else above the 10,567. So we have found an outlier. However, there is an observation, an observation above the upper fence. The claim of $21,147 is an outlier. So if we were graphing it, we would include that little asterisk. Alright, so there's how you find any outliers. Till that to the next person you meet at the bus stop. Alright, so that's it. Please email me if you have any questions on the homework. As usual, learning to do the things by hand is what I will be grading you for on your exams. For the homework, you can use StatCrunch, your computer, or any Excel spreadsheets, but for the exam, I will be asking work to be done by hand. What that means is that your data sets will be small, so don't worry about that.